Hello, today I'll be talking about the direct product theorem for quantum communication complexity with applications to device-independent quantum key distribution. This is joint work with Rahul Jain, who was my PhD advisor at CQT Singapore. Okay, so what is the direct product theorem? Essentially, it's about the question of how much harder it is doing n independent instances of a task compared to doing one instance. So if you have an algorithm for doing a single instance, you can run it independently for each instance of the task. This is obviously a naive way of doing n instances, but is it the best we can do? If you have a direct product theorem for the task, then that says that yes, it is. Now, what this means is that if C amount of resources in whatever computation model is required to do one instance of the task, then Cn resources are required for n instances. And if your algorithm costing Cn resources has 1 minus epsilon success probability for one instance, the success probability for n instances is 1 minus epsilon to the n. We'll be looking at direct product theorems in communication complexity and related parallel repetition theorems in non-local games. So let us see what those are first. In the non-local game setting, you have two spatially separated parties, Alice and Bob. In the quantum case, share entanglement. In the classical case, they just share randomness. And they receive inputs x and y that come from a distribution mu. There's a known predicate on x and y and output sets a and b. And Alice and Bob have to output small a and small b such that this predicate is satisfied. They can do this by doing measurements on their parts of the shared entangled state according to their inputs. Their probability of winning the game for a particular strategy is computed over the distribution mu on x and y and the output distribution that the predicate is satisfied. The quantum value of the game is the maximum winning probability over all strategies like this. This can be easily generalized to more than two parties. Since we don't measure resources used to win the game, the direct product question here, also called the parallel repetition question, is if the quantum or classical value of a single copy of G is P, is the winning probability of n independent copies of G P to the n. This question is of great interest in computer science because non-local games are used in lots of places. For example, parallel repetition theorems are used in hardness of approximation results, and they were used in the recent MIP star equal to RE result. More relevant to us will be their use to prove parallel security of device-independent QKD protocols. There are several known parallel repetition results. Ras first showed a parallel repetition theorem for the classical value of general two-player games, and the proof was subsequently simplified by Hollenstein. As you can see, the parallel repetition result is not perfect. If in the exponent you see this log AB, which are the size of the answers the players give in the game, and this is in fact necessary. For games with more than two players, a general parallel repetition theorem is not known. Results are only known for special types of games. In the quantum case, even for the two-player games, parallel repetition theorems are known only in special cases. For example, Jain, Peresleni, and Yao showed parallel repetition theorem for games with product distributions, and Bavarian, Wittig, and Yuan showed a parallel repetition theorem for games with anchored distributions. Although I should note that both of these can be extended to more than two players, and these special cases are often enough for applications. For example, the anchored parallel repetition theorem due to Bavarian, Wittig, and Yuan was used to show the MIP star equal to RE result. Okay. The communication setting, like the non-local game setting, has two spatially separated parties who share some resource such as randomness or entanglement. Generally, people study functions or relations in the communication complexity setting, but to keep the analogy with games, we'll stick to predicates, which are more general anyway. After Anderson and Bob receive their inputs from X and Y here, they send messages back and forth to each other, and then at the end of sending messages, they output A and B as usual. This is called a communication protocol. The communication cost of the protocol is the number of qubits communicated. Now you can consider two settings. Their success probability is computed as the worst case probability over inputs that their output satisfy the predicate, and your quantum communication complexity with error epsilon of V is the minimum communication cost of a protocol that computes V with success probability 1 minus epsilon in the worst case. Or you can consider the distributional error with respect to distribution mu, and then you define your distributional quantum communication complexity as the minimum communication cost of a protocol with distributional success probability 1 minus epsilon. There's a famous result due to Yao that says that the worst case communication complexity, not just quantum but also in the randomized setting, as long as Alice and Bob share randomness or public coins, is equal to the distributional complexity maximized over distributions. Like games, this communication setting can also be generalized to more players. The direct product question for communication is as usual. If C communication is needed to achieve success probability P for a single copy of V, is Cn communication needed to achieve success probability P to the n for V to the n? Direct product results in communication can be used to give communication lower bounds for specific functions. And communication lower bounds are obviously connected to many other models of computation. They can be used to show time-space trade-offs in the Turing machine model, for example. Direct product questions in communication have been extensively studied, and I'll list a few results here. For bounded round quantum classical communication, strong direct product results are known due to Jain et al. And then Braverman et al. In the quantum case, though, results are more limited. We showed a strong direct product theorem for one-way quantum communication recently. Earlier, Shurstov gave a direct product for communication in terms of the generalized discrepancy method, which is a lower bound technique on classical and quantum communication, even with unbounded rounds. But this only works for two-party and Boolean output functions. Now we come to our results. Our main theorem is a direct product theorem for quantum communication for any L-party predicate V. The statement is somewhat complicated. It's in the distributional setting. We consider a product distribution mu on inputs for a single copy of V. And also we take a protocol for n copies of V that have communication Cn. Our result is stated in two separate cases. If C is less than 1, we showed that the success probability of P under mu to the n goes down exponentially in n, with the base of the exponent being this factor that depends on the value of the game corresponding to V and the distribution mu, and also the communication C per copy. The omega in the exponent here hides factors depending on output size, the same ones that appear in all the parallel repetition results. This result is obviously useful when C is pretty small, comparable to the game value, and it should be interpreted this way, that a parallel repetition theorem for a game holds even if there is a small amount of communication between the players. Our result in the second case corresponds to the true communication scenario when C is at least 1, but upper bounded by the log of something called the quantum partition bound or efficiency of the predicate V. So this is a lower bound on communication. And in this case, we show that the success probability goes down exponentially in n, with the base of the exponent only depending on what error parameter you choose for the efficiency, etc. Okay, so case 2 of our theorem is a proper direct product theorem for communication, like I said. Since the result only works for product distributions, however, it gives us a direct product theorem for interactive quantum communication in terms of the max efficiency over product distributions. Even though we can compare efficiency to a distributional version of generalized discrepancy, Shurstov results also work in the non-distributional setting, which makes our result not directly comparable to his for two-party Boolean functions. But on the plus side, our result also works for more than two parties and non-Boolean functions and predicates. As an example, efficiency for a product distribution exactly characterizes the quantum communication complexity of the generalized product inner product function, which is defined over any field instead of just F2. So our result gives a strong direct product theorem for generalized inner product. As an application of case 1 of our result, we show that it is possible to do device-independent quantum key distribution in the presence of leakage from the parties' devices. Specifically, we show that a DIQKD protocol given by Jain, Miller, and Shi, based on the magic square non-local game, is resistant to leakage. Our result specifically is like this. There exists some C0 such that if you have Cn leakage for C less than C0, when doing the protocol with boxes compatible with n copies of the magic square game, then you can extract some Rn amount of key from the protocol where R depends on C and the expected noise level delta of the boxes. Okay, now I'll explain how we get our result in a bit more detail. First, I'll explain what this efficiency or quantum partition bound is. The quantum partition bound is related to zero communication protocols. The zero communication protocol is one in which either party can abort, but condition on no party aborting, the protocol has to be correct with high priority. The efficiency of such a protocol is the inverse of the probability that it doesn't abort. Laplante, Larraise, and Roland introduced the quantum partition bound, which is the maximum probability of not aborting or the minimum efficiency of a zero communication protocol that computes B correctly with respect to a distribution mu. And they showed that the log of this is the lower bound for the distributional quantum communication complexity uh, with other distribution mu. Our direct product proofs are done in a standard framework for direct product and parallel repetition theorems, which was introduced by TAS. So how it goes is that we'll consider a strategy for P to the n, which has communication Cn, and we'll consider a subset S of the n coordinates. And we shall show that one of the two following conditions holds. First is that the success probability in S is already as small as we want, so we are done. Otherwise, we show that there exists a good coordinate I that is not in S, such that the success probability on I conditioned on success in S is bounded away from 1. So then we can build up a sufficiently large set whose success probability is small inductively. How the existence of this good coordinate I is shown depends on what kind of result you're trying to show. Uh, in case 1 of our theorem, we shall show that if the success probability of I conditioned on success in S was not small, then this gives us a protocol for a single copy of the KMG V mu with the success probability more than the quantum value of the KMG, which is a contradiction. In case 2, we shall show that if this conditional probability is too large, then that leads to a zero communication protocol for a single copy of V with efficiency 2 to the C and error probability condition on not aborting being epsilon. This is also a contradiction if C is smaller than the log of the efficiency with the error parameter epsilon. Before I give any more details of our proof, I'll explain how the proof of parallel repetition for product games goes. This proof is due to Jain, Paris, and Yao, and it will be quite relevant to our proof. So, condition on success in the subset S for a protocol for G to the n, we can define a certain useful state phi that represents the global state at the end of the protocol conditioned on the event. For all the coordinates I outside S, phi contains xi, yi, ai, bi in superposition, where ai, bi are Alice and Bob's answer registers. And the state phi is such that if you measure the ai, bi registers on phi xi, yi, you will get a conditional distribution p hat ai, hat bi condition on xi, yi. Then the overall distribution of xi, yi, hat ai, hat bi is close to the distribution of xi, yi, ai, bi condition on success uh, uh, in S in the protocol. Now, for a good coordinate I, it's possible to show that Bob's half of phi, which includes the YB registers as well as some other registers, does not depend too much on Xi. That is, phi of Bob condition on Xi is close to the state averaged over Xi. This is because the states without conditioning on success in S were equal because of the probabilities because of the product distribution. And conditioning on success does not disturb the state too much if the success probability is high. Similarly, phi of Alice condition on yi is close to the average state phi of Alice. This means that in a strategy for a single copy of G, Alice and Bob can share the pure state get phi as their shared entanglement. And because of these closeless relations that I just described, there exist unitaries uxi and byi that they can apply on their share state on getting inputs xi for the single copy KMG, such that the resulting state is close to phi xi. Then they can measure the AIBI registers of the state. Their output distribution will be close to PXI YI AIBI condition on success in C. Condition on success on S. And therefore, if the probability of success in I condition on success in S is high, their probability of winning is also high. Their proof easily generalizes to more than 2 pairs as well. And as it turns out, basically the same proof works even if you have small communication. You just have to define the state phi appropriately using the state at the end of the communication protocol, and your closeness relations will depend on C. So our direct product proof in case 1 is very similar to this. In case 2, on the other hand, since there is a lot of communication, you can no longer say that phi of Bob condition on xi is close to phi of Bob, or the same thing for Alice. But if Alice communicates C1 n bits in the protocol and Bob communicates C2 n bits, then we can say that the mutual information between xi and Bob and phi is about C1, and the mutual information between yi and Alice is about C2. Now, to give a zero communication protocol, we shall use a message compression scheme that is apparent from the quantum substrate theorem. So this was given by Jain, Radhakrishnan and Sen, and it says that if we have a mutual information bound between x and b and phi, then there exists a state phi prime xp close to phi xp such that phi prime xp is upper bounded by 2 to the O of c times phi x tensor phi b in the operator inequality sense. And this in turn means that given any purification get phi of phi, there exist projectors phi x acting only on Alice's system, such that if you do the measurement pi x and identity minus pi x on get phi, pi x will succeed with probability 2 to the minus c. And also the post measurement state after the success of pi x is close to get phi x. This suggests an obvious zero communication protocol like this. We know from the mutual information bounds that projectors pi xi and pi yi taking get phi close to get phi xi and get phi yi exist. So maybe Alice and Bob can share get phi as entanglement, and on getting their inputs, they apply the projectors on their respective halves of the state. We hope that both of these projectors will take get phi to get phi xi yi with probability 2 to the minus c1 plus c2, since the projectors individual success probabilities are 2 to the minus c1 and 2 to the minus c2. But this does not work out as straightforwardly because pi I does not succeed on the state after the application of pi yi does not succeed on the state after the application of pi xy in superposition over xi with high probability. Remember, this state is only close to phi xy, not xi, not exactly it. And unless the closeness between the state is of the same order of magnitude as the success probability of pi yi on phi, we can't say anything. In order to deal with this, we need to develop a new tool, which we call the substrate perturbation lemma. This says that if phi prime ya is upper bounded by 2 to the c times phi y tensor phi a, like we have from the substrate theorem, then we have another state rho a which is close to phi a. And there exists another state rho a which is close to phi a. Then there exists a state rho prime ya that is close to phi prime ya, such that rho prime ya is upper bounded by 2 to the order of c times phi y tensor rho a. Now we can apply this theorem with rho a being the state after the application of pi xi, and we get a different projector pi prime yi from the resulting state rho prime yi on Alice's system. If we do the protocol with this projector, then everything works out fine. Okay, finally, so I'll briefly talk about the QKD application. So key distribution is a cryptographic primitive where two honest parties, Alice and Bob, both get a uniformly random key K, which is secret from a third party eavesdropper Eve. This can be done with information-theoretic security in the quantum case. For example, QKD protocols can be based on non-local games. The idea is that Alice and Bob share some resource and play a non-local game. If they are able to violate a Bell inequality in this game, that is, if they are able to win the game with probability higher than its classical value, then that means there must have been a shared entangled state between them, no matter if Eve tampered with the shared state or not. And this shared entanglement can then be used to get a key that Eve has no information about. The device-independent framework is the most paranoid type of framework for quantum cryptography, where the honest parties are not required to trust shared states like this, and they're not even required to trust measurements that they're performing on the shared state. Device-independent protocols are always based on non-local games, but the thing is, if you want to use non-local games for your security analysis, you need to require that there will be no communication between Alice and Bob and Eve's quantum devices. So that has always been a requirement for QKD protocols, but this is not so easy to ensure in practice. So yeah, we give a proof that it can be done even with communication and show it specifically for a parallel QKD security proof given by Jain, Miller and Shi, and also we did based on parallel repetition. So specifically their proofs use a three-player game between Alice, Bob and Eve in order to get a linear key rate. Now in our result, we have a fully interactive leakage model, meaning that Alice, Bob and Eve's boxes can all communicate with each other in arbitrarily many rounds. We'll simply put a bound on the total amount of communication. This scenario is now modeled by communication complexity rather than non-local games, and case 1 of our theorem applies. Using this, we can show that the key rate of with leakage is what the key rate would be without leakage, as shown by Jain, Miller and Shi, minus order of square root c times n. Okay. So to conclude, the main takeaway from this talk should be that we prove a direct product theorem using zero communication protocols, and our technique works for L parties as well as predicates with any kinds of outputs. In order to do our proof, we develop a new technical tool called the substrate perturbation lemma, which may be of independent interest. And secondly, we prove that a parallel repetition theorem for non-local games holds even if there is a small linear amount of communication. And using this result, we prove that it is possible to do quantum cryptography even in the presence of linear leakage. This brings me to the end of my talk, and thank you for listening. I'll be happy to take questions later. Thank you.